Welcome to EDU World Space.
For question 100 in chapter 22, we are tasked with finding a series of bond enthalpies for an H oxygen bond, an H sulfur bond, an H selenium bond, and an H tellurium bond. And what we're given is a whole bunch of enthalpies of formation. And it may not look like that immediately, so I'm going to review those really quick before we get into solving this problem. So let's look at the enthalpies that we're given. We're given the enthalpy of formation for H2O gas. H2S gas. H2SE gas. H2TE gas. And a bunch of other stuff that says that given these elements, or we're given the enthalpies to form these elements, a mole of these elements in the gaseous phase from their elements in their standard state. So that's the same thing as enthalpy of formation. So just an oxygen atom in the gas phase. And then going down the list once more of sulfur, selenium, and tellurium. (197 kilojoules per mole). All right, so this is all the information that we're given. Oops, I should have included the phase for these. These three are gaseous as well. All right, so the approach that we'll want to take for this is we'll want to do a Hess's law approach. Ultimately, we're looking for a reaction we're going to construct a reaction where all that happens is we break two bonds to form the elements in their gaseous state, because delta H of the reaction is just the sum of the delta H of formation of the products minus the same thing for the reactants. So we're just going to construct a reaction for each of these four cases where we take something like H2O and break it down into just isolated gaseous hydrogen atoms and isolated gaseous oxygen atoms. And that enthalpy will be the enthalpy of breaking two HO bonds. So for example, we're going to build this reaction and when we do that, we'll essentially have the energy required to break two HO bonds. And so if we get the enthalpy of this reaction, then divided by 2, we'll have our HO bond enthalpy. So let's go take a look at how to do that. So to do that, we are going to simply take the enthalpy of formation of our reactant here, and then it'll be the negative of that because it's a reactant. And then we'll just add up the components of all the products. And there is an additional enthalpy that I did not include, which is the enthalpy required to break apart two gaseous hydrogen atoms. So I'll add that to the list over here. So the enthalpy required to go from H2 gas to two hydrogens, and that's going to be 436 kilojoules per mole. So for this reaction, what we'll be doing is we'll just take this reaction up here, H2 gas, because this is hydrogen in its standard state, so the heat of formation of two hydrogen gases in our products, plus the heat of formation of an oxygen. And then in the reactants, we'll use H2O gas, the heat of formation for that. So let's add another page here. So we need the enthalpy of the products. So the enthalpy of the products, we've got these two hydrogen gases. That's going to be the enthalpy that we'll be using for that is the enthalpy for this reaction. And then for this oxygen, we'll just be using the enthalpy of formation for a gaseous oxygen atom. And then here we'll be using the enthalpy of formation. I should mention that these are all supposed to be in standard states as well, so I should be using this superscript. So the enthalpy of formation of our products then will be this 436 plus this oxygen atom, which we said was 248 joules per mole. Then we're going to subtract the reactants. And for H2O, that was the enthalpy of formation was minus 241.8. So joules per mole once again. Okay, so what do we get when we do all that? We get where'd that line come from? We get 925.8 kilojoules. And then kilojoules per reaction unit. And so therefore, the HO bond dissociation energy will be this divided by 2. Because this reaction that we're showing up above here is the breaking of two HO bonds. Oh, I should include my kilojoules per mole. So that's just for the HO bond dissociation, but we can go on and use the exact same approach for all of the other ones. And I'll write that out in detail here. So the next one will obviously be H2S. in the gaseous phase going to a pair of hydrogen atoms plus a gaseous sulfur atom. And using the same mathematical approach of products minus reactants, our products, again, we're going to have that reaction with the the H2 gas going to 2 gaseous hydrogen atoms. So that'll be 436 kilojoules per mole, plus our sulfur, which, as we recall originally, was 277 kilojoules per mole. And then our reactants, which were, if we go to here, so its heat formation was minus 20.17 kilojoules per mole. So the enthalpy for this reaction and of course, we want to divide this by 2. So when we divide this by 2, we get for our bond enthalpy 366.59 kilojoules per mole. And again, that's because here we've broken 2 HS bonds. And so if we take the enthalpy of this reaction and divide it by 2, then we have the enthalpy of breaking a single HS bond, approximately. All right, so let's move on to selenium. Same approach. All right, so once again, products minus reactants. And once again, with the hydrogen. So going back, this time we're going to be using, once again, this reaction. So 436 kilojoules per mole. Then the selenium as our reactant. And then over here, our gaseous selenium as a product. And I'm going to omit units on this one just for the sake of brevity. Okay, so this here is our hydrogen, our selenium, and then we're going to subtract our reactants. And divide by 2. And we get this bond enthalpy of 316.65 kilojoules per mole for the selenium. And then lastly, for the tellurium, got gaseous H2Te going to two gaseous hydrogen atoms and a gaseous tellurium atom. And the enthalpy of this reaction is just the enthalpy of formation of the products minus the enthalpy of formation of the reactants. So we're going to use our formation of gaseous hydrogen atoms again from the H2, the standard state. Then the gaseous tellurium, which is over here, 197 kilojoules per mole. And then we're going to subtract off the reactants, which is our H2Te. So that's going to be over here, right there, 99.6 kilojoules per mole. And the enthalpy of this reaction is 533. 0.4 kilojoules per mole. And therefore, our bond enthalpy for the HTE bond will be this divided by 2, 266.7 kilojoules per mole. Okay, so now we've got all of our bond enthalpies. We've got the HO bond association energy of 462.9 kilojoules per mole. Then we've got HS at 366.59, HSE 316.65, and HTE at 266.7. So let's just kind of round up all of those answers into one place so that we can have a good look at them. So for our hydrogen-oxygen bond, 462.9. And these are all in kilojoules per mole. So we're just going to put that at the top of our table here. For HS, it's 366.59. $316.65. And 266.7. All right, so actually, it's very convenient to have them laid out this way because this is actually the order in which they appear top to bottom in the periodic table. And if we look at the trend of these, you can actually see that this order I have here is in increasing atomic radius for the second element. So we'll say non-H atom radius. As we increase the radius of this second atom to which the hydrogen is bonded, we can see that the enthalpy required to break that bond also decreases, which makes sense because shorter bonds are in general tighter bonds. So we see weaker bonds with increasing atomic radius of the second atom. Okay, so in summary, what did we do for all of this? In summary, we said that we wanted the bond enthalpies for all of these different hydrogen, whatever bonds, hydrogen, oxygen, hydrogen, sulfur, what have you. And we noted that we were given standard enthalpies of formation for all of these different hydrated species, and also that we were given the enthalpy required to form gaseous atoms of these species as well, from elements in their standard state, which is also an enthalpy of formation. So we used a Hess's law approach, using delta H of reaction as just the enthalpy of formation of the products minus the enthalpy of formation of the reactants. And we constructed all of these reactions and solved them using Hess's law and compiled a list. And we found that when we put everything into a table, we can see that the energy required to break these bonds is lower with increasing radius of the second atom. So larger so the larger the radius, the weaker the bonds it forms to hydrogen. Okay, thank you, and I hope that was helpful.